because unfortunately I can't speak French or Arabic, and I hope everybody expects that from the program. So let me introduce once again. I'm Ondro Mihályi. I work for Pyar Services, and mostly I work with a community on open source projects, and Pyar also is an open source application server. But this presentation is about about using distributed data grids to power scalable applications. And what do we mean by scalable applications? It's a term you can see very often on blogs, on the internet. Everybody talks about it, writes about it. It doesn't really mean something, or it was already there. It's just a new marketing word. And highly scalable applications. You often see these two together. Everybody talks about speeds, like how your applications can benefit from cloud and high loads. They have to be highly scalable. But what does that actually mean? How we can achieve that? So, we can either play bingo, buzzword bingo, or try to find out what's in it, what it really means. And it's not easy to separate all the marketing stuff from the real meaning of that word. So I'll try to explain. The main goal of scalability is to build applications that can consume the resources we throw at them. We give them more CPU, we give them more memory. They can benefit from it and increase processing speed, improve performance. That's the word, scalability. The application scales to meet the demand, the increasing demand, and it doesn't scale just like that. It scales because we give it more power. Some applications can leverage this power and increase performance, and those applications are scalable. Some other applications can't leverage the more resources, and the resources are just lying there. The application cannot consume them because either they are single-threaded applications or they don't parallelize so much. And it also works the other way. If we don't need that much power from the application, that much speed, we don't want to pay for the additional resources, so we take them away from the application, and the application scales down. So it's both ways, up and down. Pretty much. So as I said, this is not always straightforward. You have to design applications to be scalable most of the time. It's the same thing as with single-threaded and multi-threaded applications. If you write an application that runs only in a single thread and everything is sequential, you can't use more threads because the application just wouldn't use them. Even if the CPU has more cores, even if the operating system can provide more threads, the application wouldn't use them. You would have to start more applications of the same more instances of the same application to run on a different thread. And the same thing is with when you go to cloud, you can parallelize processing on different machines. You can dynamically improve CPU performance and memory. The application has to somehow consume this. And we have two types of scaling. One is vertical and the other one is horizontal. It's really easy to get confused with these terms, and I always very often got confused. I don't know which one is which until I imagine that horizontal is at the same level, so it grows by adding more and more more power next to it, and vertical is growing up. So, for example, CPU grows up when you instead of a slow CPU, you put the application on a faster CPU. You get more megahertz, more gigahertz of processing power, so it goes up. It's vertical. But when you put more CPUs next to each other and the application can just jump to any of these CPU and use all of them, that's horizontal scalability. And this horizontal scalability is much more powerful because we reach the limits of how much we can increase the power on one node, on one processor, one system. And it's much easier to just add another one and grow a farm of computers. That's basically what's cloud about. Cloud provides many instances. If you want to have one instance, a very powerful instance is very expensive, because when you want to get to the limit or slightly over the top, you have to pay for the supercomputer. It's big vast of money. But when you just buy hundreds of cheap machines, it's not that expensive, because they are just created in factories every day. So we're going to focus on horizontal scalability, because the vertical one is quite straightforward. We just add more expensive CPUs, more expensive resources. But with horizontal, we can add just the same thing multiple times, and can also reduce it. It is much easier to scale up and down with horizontal clustering, horizontal scaling. But also, there are some downsides coming from when we want to horizontally scale application. And these downsides come back to the analogy of single-threading and multi-threaded applications. It's basically parallelism. Parallelism is always there when you want to scale horizontally, because you have more similar instances of the application running on different nodes, and they either process every request autonomously, so you don't have to share information, but very often you need to share the information and coordinate. You at least have to have a load balancer which just routes the request to the nodes that are available. So there's more complexity when you design for horizontal scalability. You have to communicate among these nodes, and it's much harder to do when you communicate across network than when you communicate across threads or even in one thread. So every time you go more and more parallel, you get more complexity. And also, when you don't design the communication well enough, there can be big communication overhead. When you have multiple nodes and every node communicates with each other with a not very clever algorithm, then you can add more resources to the application, but the application will still wait on messages coming and messages being sent, and it will be starving on these messages. You know that when you have the topology where everything communicates with everything, the amount of communication grows exponentially. And now when we come to one observation coined by Amdahl, which basically says that it's not enough to increase throughput or increase parallelism in one part of the application. We always have to think about an application as a whole, because every small part of the application which is not able to consume the power, which is not able to be run in parallel, it would limit the potential of the whole application. We can improve the application one at a time. We don't have to improve all the application at once. But until we improve whole application, there is still some limits onto which we can parallelize and benefit from horizontal scaling. And here, down there, are all the bottlenecks that are examples of the bottlenecks that can be in our application. Every time we see some sequential processing in the application, it's a bottleneck, because it can't be parallelized. It wouldn't help to add more CPUs to process this pipeline, because it has to run one after the other. And synchronization and communication are already talked about. So one solution to this is to use in-memory data grids. Data grids are basically distributed memory, and also a lot of them provide other distributed structures like distributed logs. or these queues, which are very easy to use because they seem similar as you already know them. Like queues provide the interface to send an object to a queue and then receive it on the other side of the system somewhere on a different node. But in reality, if you would like to implement this yourself, it's really hard. And the reason it's hard is because there's lots of asynchronous communication going on, and you have to maintain some how do I say it? You have to make sure that everything works as you expect. In the world of too much parallelism, you can never easily ensure that a message is received by one of the nodes when you send it, because each time a node receives a message, it has to basically ensure that no other node receives the message. When you have memory, you have all sorts of problems when you implement yourself. Either you distribute every item on every node, and then the memory grows up, because every time that you put some item in the distributed memory, it gets distributed on all the instances, and basically you use a lot of memory. Every instance, the memory grows. By when you add one item on one instance, it goes on all the others. And clever data grids solve this problem. They provide replication of the data, so that the data is distributed. If one of the nodes goes down, the data is still there, and other nodes can access it. And when the node goes up, it can still receive the data. So in some sense, it's also a highly parallelized and fast database, or at least NoSQL database in some sort of sense. And the other thing is what these data grids do. They distribute the data not on every node, but cleverly just on some nodes, enough to ensure that there is some resilience in the data, that the data is still there if at most some of the nodes fall down. So for example, you have 10 nodes in the cluster, and you may configure you want to make sure that if 3 of those 10 nodes suddenly fall down, the data is still there. If 4 of them at the same second go down, you may have some data loss, but there is a trade-off. You save the memory, and 3 nodes are quite, or 4 nodes falling down at the same time are quite improbable. And if it's not on the same time, the data grid will detect all those fallen nodes, missing nodes, and will redistribute the data in a couple of seconds among the rest of the nodes. So then at least it would take at least 4 more nodes, plus the one that fell out, to take down some data. Because the data is already, after a couple of seconds, is already on at least 3 other nodes. This is sort of algorithms you wouldn't want to program yourself. So there are already solutions to this, quite a lot of them, in fact. Some of them are more clever than the others. And here are some of the examples, not all of them. I would say that there are maybe 20 well-known solutions. Some of them are open source, like Hazelcast. And in fact, Hazelcast is a solution also used in PyR Server and PyR Micro. PyR Server is an open source project. It's originally an application server derived from Glassfish. And the advantage of incorporating Hazelcast into the application server is that you get a lot more features than the data grid. You get a whole programming framework for writing applications and business logic. While Hazelcast is just a data grid, like distributed memory, you still have to write your application and save data to it. So for writing applications, PyR Server and Hazelcast are a good match. PyR Server providing all the API, like for creating REST endpoints, for accessing databases, and Hazelcast provides distributed memory to distribute HTTP sessions. It provides a JCache API for your application to programmatically save some data to cache. And Pyre also exposes Hazelcast itself, the Hazelcast API, so that you can access other Hazelcast specific things like distributed queues, logs, and distributed structures. Pyre server also builds a lightweight messaging system on top of Hazelcast queues, which uses CDI API, CDI events already present and specified in Java EE specification. So some of you may already know CDI events, and then it takes only using two annotations to send a message across the cluster to another node on the Hazelcast cluster, and the second annotation to receive that message. Everything is handled automatically then by Hazelcast. Pyre Micro comes from the same source code as Pyre Server, and it technically is an application server, but I prefer calling it a runtime because you execute it from the command line. You don't have to pre-install it before and deploy applications on top of it. You can just have your application as a WAR file, download Pyre Micro, and run it from command line just with a simple command line. And everything in Pyre Micro is geared towards using in cloud and these flexible clusters. So Hazelcast is turned on by default, which isn't the case for Pyre Server. In Pyre Server, you have to turn it on if you want to use Hazelcast for clustering. So now it's the time to do some, or to go through some cases how you can scale up your application without reprogramming your application. If you design your application for scalability, then you don't need to modify your application, or maybe you would need because you don't know what to expect later, but there would be much less effort in improving your application to make it scalable in the future and distribute the memory. So now to explain, I'll show you some code, what is necessary to turn a normal application. Yes? Okay, so question is if it's transparent to use Pyre Server with your application. Pyre Server is, we may compare it to Tomcat, but more like to other Java EE servers because it provides Java EE API, like WebSphere, WebLogic, or Wildfly. And if you design your applications according to Java EE standards, all of the servers support the standard, so you don't need to modify your application. You just deploy it on Pyre Server. Plus, if you want to use caching in Hazelcast, you can either depend on JCache, which is again a standard, but not yet part of Java EE, so it's not supported by every server. But also, for example, Spring Framework has a binding for JCache and integration to JCache. So you're locking yourself to one technology. This is just an API that is provided by Hazelcast, but you can also remove Hazelcast and put in some other implementations. Some of the implementations for JCache are local, so the cache is not distributed. It's only in your virtual machine. And Hazelcast is one of the implementations which can distribute the memory across the mountain. Hazelcast itself runs on JVM and Pyre Server too, but there are client bindings for other languages, like one of them is for JavaScript. The other language, when you access Hazelcast from other languages, they won't become a member of the cluster, so they don't hold the memory, but they can access it from another JVM node. So it works like a database. You connect to the cluster, get the data, you can put the data there. So it's more like a database. With Pyara server, you can put the data and get the data with just Java API. You don't have to connect to it because Hazelcast is already present. With JavaScript, you have to connect, so you have to specify the IP address of one of the instances, and then you can just get the data and communicate with the cluster. I have a demo here. I'm not sure if I will have some time, but I have an application which runs on Pyara server, and one service that front end is running on Node.js that accesses this Hazelcast cluster from JavaScript. So in Java, the API can be used either with JCache or injecting a Hazelcast instance and using Hazelcast itself. This is just one REST resource. There's nothing about JCache, nothing about Hazelcast. It just works with an entity called schedules. It's like a conference schedules. When a talk is, where it happens, in which room, and some other details. And the rest provides one method to retrieve all the schedules and parameter count. So not all the schedules, but only first count schedules. And it accesses DAO, which in the first version is just DAO, which gets all schedules from some memory, from file. It gets all the schedules from file and then limits them to the parameter, puts some sleeve there to demonstrate it's slow to emulate the database access. But what we can do with this default implementation with very, very few lines of code is if we use CDI for dependency injection, you can see I injected the schedule DAO, the object that provides the data, manipulates the data, using dependency injection, using inject. So normally it would inject this object. But with CDI, there's a concept of specialized beans, which basically replace the original bean. So if we use this caching or cached bean, which extends the original one, and the specialized annotation turns it on, so it replaces the original one with a new behavior, we can wrap the original behavior into a caching mechanism. And the caching mechanism is twofold. The easiest way is to cache result. We can also move this annotation to the original one if we don't use this specialization. I wanted to use it to show you the difference. But we can use this cache result annotation with any CDI bean. And what it in fact does, it's an interceptor that first asks the cache if it has the data. It will get the parameter name of the method and will see if this method was already called with these parameters. And if yes, it will automatically return the cached value. So it won't even call the method. That saves execution time, and it's already, if we use Hazelcast, which is distributed, the memory is already available on all other instances. So we can scale it, and first time the method may be called on one instance, but then if we execute it on another instance, the retrieval of the data is much slower because it only has to access the cluster. It doesn't have to go to the database, which is much slower. And this is for automatic caching. If we want to implement some more logic, we can inject cache implementation. This is still part of the standard of JCache. There is only one configuration annotation specific to Pyara, which specifies the name of the cache, but it's not necessary to use it. It would automatically generate the name of the cache. Here it also enables statistics and management. What it means, you can see some information about the cache through JMX interface. JMX interface is available, let's say, through JConsole or JVisual VM plugin for seeing managed beans. And when we connect to our server, there is, I need to put something in the cache, I guess. So I'll access the cache, access these rest points. So it's the first time it took 3.75 seconds. When I execute it again, it's 100 milliseconds because it caches the data. And now when we, yes, it's already here. I'm not sure if I can increase the font. Unfortunately not. But I'll show you more details later. It just you can see this is a low-level data which you can access, and this is also specified by the specification. So every JKit implementation should expose this data, or at least these places where the data are, so that you can you're sure that they are there. Hazelcast itself also provides a lot more information via JMX, so you can see other information, other statistics. But I won't show you this. Later I will show you a graph, taking these numbers and showing the relevant data in visual graph, so you can see it better. But now you saw the improvement in speed, in speed of processing. And with this way, as I said, we can scale up the application, the memory is distributed, and when we load balance, we don't need to isolate the request, because every request will have the data if it's executed on one node or the other. And it's just a couple of seconds. It depends on how fast your network is, but a couple of seconds or milliseconds when the data is distributed. So it sometimes happens that when requests are very fast ones after each other, it takes some time to distribute the data from one node to the other, but if they are not like very fractions of milliseconds fast, one after the other, then it's pretty safe. Yeah, so another layer of caching is to use, or another layer of using distributed data is use the Hazelcast distributed maps, where the difference is that the use case for cache is just for caching temporarily. You never know when the data will move out. You can specify policies. For example, the data should be moved out of the cache after 5 minutes and then have to be refilled again. But even if you don't specify the policies, it's up to implementation how long it will leave the data in the memory. If you really want to store them in the memory and safely so that they remain there, you would either put them into an HTTP session for the scope of the session and configure by a server to use Hazelcast to distribute the data there, or you can access Hazelcast directly. And this is what I do in another example. It's just basically the same. It again retrieves the data from database if the data isn't there, but if it's there, it stores them in a map, but it remains there. So it's basically eternal until I clear the distributed map. In this way, I can work primarily with the distributed map as a database, and use the SQL database or whatever other persistent database as a backup. There is also a way to start with the Hazelcast and attach some event listeners, so that every time you remove or you put something in the map, it's also transferred to a database. And then you get still get the performance improvement. So when you retrieve the thing, it's already in the map. It doesn't go to the database. But you can extend the distributed memory with read-through and write-through mechanisms to store the data in the persistent database as a backup. So you can play with it in any way. But here, basically, I decided to use Hazelcast as a distributed database. And to work with Hazelcast, in PyR server, you can inject it with a resource annotation as a Hazelcast instance. And Hazelcast instance can be used to create a map, and you name the map. And when you create a map, the advantage of doing this is that the map can be accessed from JavaScript or from any other client. JCache is only Java specific because it was designed for Java, for Java language and for Debian usage. So, and Hazelcast implements it as a separate structure and doesn't provide bindings from JavaScript or in other languages. So if you really want to use a cache that is accessible from other languages without your application creating a proxy, you can also create an API in your application to expose the data to other services. But if you want to directly access Hazelcast from, let's say, JavaScript, it's better to put the data into a map, and then it can be accessed from JavaScript. You still have some issues regarding serialization, because you have to convert Java objects to JavaScript objects. You either provide some JSON serialization mechanism, but it's possible. So this is what we got here. We improved our application and made the memory available across the cluster. But I don't know how much time we have. Okay. But there are more ways how you can manipulate with the cluster and with the configuration and to scale your application. One is basically multiplication with horizontal clustering and distributed memory. You can spawn more instances. You have the memory available in all instances, and you just need to put a load balancer before them so that it distributes evenly the requests. That's what we talked about. But one more option is or one issue you will come to is that you may have a lot of data in memory, and you have, let's say, 5 instances in the cluster. The memory fills up because it's stored on the heap, and you usually limit the amount of heap memory used in production. And if the memory is used, then you don't have any memory for normal processing. If you want to reduce the usage of memory, you can use one pattern, which is to spawn more instances, but without running your application. They will just extend the cluster. They will remove some memory from the instances that have your application, that power your application, reduce the memory on those instances, and move them to other instances. To illustrate it with PyR server, it would look like this. There are some nodes which I call active because they have the application. Any one of them can serve requests. And then we can spawn more nodes, either as PyR servers, but what is more convenient now is PyR micro, because you can spawn it from command line and you can just run it in Docker. There are also Docker images for PyR server, which basically provide the same thing. In Docker it doesn't matter because you just run the Docker. But if you run them locally or just without Docker, it's much easier to run PyR micro. And now they connect to the cluster and the memory is distributed, so there's less memory consumed here and more consumed here. Another use case is this is more or less specific for Hazelcast, is to separate the nodes that have the application and move all the memory to other nodes which are not active, which only provide the data. And you can do that only for mission-critical applications if you have more applications in the cluster, or you can do that for all of them. So all the applications run only on so-called light nodes, which don't keep the data, and there are full nodes which keep the data in the cluster. They are all members of the cluster, but some of them consume only the memory necessary for the application, and the others consume the memory that is the data, basically. Yes and no. Yes and no. It would slow your application because the application has to request the data from other nodes. But it would also decrease the amount of memory in heap, so garbage collection would be much faster. So it depends. It depends. But sometimes you don't rely so much on the memory, so you get the memory first, and then you have to do a lot of computation. And then it's good that you have all the memory only for the computation, and the shared memory is somewhere else. But when it's all together, then garbage collection has to go through all the memory. So it's just an option how to improve the behavior of the cluster. Again, without rebuilding your application or just not going too much to the application source code, but in the configuration. So in the end, it looks like this. The distributed memory is shared on the full instances, and the light member just runs the application. And as you said, it might be slower because it has to access, every time it has to access another instance for the data, but then the garbage collection will be faster because there's no overhead in the heap. And I'll show you the demo how it works in a real application. So I have one instance of the application running on Fire server. It is the full server. It consumes slightly more memory because it also has some other services running and administration console. And I can check how many data we have in the memory. It's only 10. I'll try to increase. So I executed a REST resource which returns the number of data in memory. It's 10. But now I can generate some random data. I create 10,000 data. And here here is a graph that runs on, that is powered by Grafana, and in the background there is a collect-D process that scans the data over JMX from the server. So there is a monitoring system that scans the data about the memory, and Hazelcast provides exact metrics for the heap taken just by the Hazelcast distributed data. So it doesn't show the, I don't have to go to the heap memory statistics because you know that there is always some memory that will be garbage collected later, so it's not perfect. But this shows exactly how much memory is used by the cluster. And here you can see that the memory of in the cluster increased to 3 megabytes. These 10,000 items have used 3 megabytes. And now I will run a Fire micro instance. And after it connects, we will see another graph stacked on top of this one. What will happen, you will see, that the amount of memory doubles. Because the same memory is distributed on the, it's already here. It's distributed on another instance. And you may have a question, why it doubles? It duplicates the data. And because there are no more instances in the cluster, the data is just doubled just to make it safe that if one of the nodes goes down, the data is still there. If I run another instance, you'll see something different. The amount of data will not double, it will actually stay the same. And the reason is that it doesn't have to use more memory because everything is twice in the cluster. It will just redistribute. Wait. It will just redistribute the memory across the 3 instances, but it's the same size. So I don't know if it's the graph is correct right now, but it's the same amount of memory. If we can count all those 3 instances, it's the same amount of memory, just distributed in a more clever way. It's not every data on every node, but only every piece of data is only on 2 of those 3 nodes. And if we grow them, then the distribution will be even more across the cluster. And we can also do one thing with Fire Server, which we can't do with Fire Micro easily. We can access administration and change the node, the Fire Server node, from full member to light member. So it will basically restart Hazelcast, but the data is already in the other nodes, and it will restart it so that it runs it only in a light way. It will move all the memory to the other members of the cluster, but and decrease the amount of memory used by this JVM. So let's go to the cluster. You can see here there are all the cluster members. One of them is full server, 2 others are micro. And on the server, we will change this node to a light cluster. Takes a while until it restarts. And now we can see that the server is still running, but we only see now two nodes in the graph. And you can see the amount of memory is still the same. It's just the data is distributed from 3 nodes to only 2 nodes, and the server node doesn't consume memory for the cluster. It has all the memory available for the application. One more thing we could do, but this requires some engineering in the application, is to approach some parts or identify some parts of the application that need to be scaled differently, in a different way than the rest of the application. And this is basically the reason why we have microservices architectures, to have application distributed not only in memory, but the code is distributed into services and run in different services, and these services can be scaled separately. So one service which is used not very often, it can have only 1 instance and can consume only the resources required for 1 instance, but other services do high computation or access a lot of data from database, so we need to scale them up. And ideally, we would connect them with messaging. So, for example, Hazelcast queues, or the CDI bus present in Fire Server, or more reliable messaging like Kafka or JMS. So that when there is a message, it would be distributed to one of those instances of the service. So one slow service, which we don't need to make faster, would just emit messages once in a while. And the bottleneck would be scaled up to a couple of instances, and could parallelize the processing, or could just provide handling for more requests. in parallel. And for this, if you are already in Payara server using Hazelcast, it's wise to use Payara Micro to slice the application from the big monolith, one service at a time running in Payara Micro, and you still have the benefit of distributed memory. So you can still use the same code base and only tweak it so that it runs in a different service. But you don't have to decouple all the code and all the services at a time. It's a good pattern to decouple them. So eventually, if you have a lot of enough money and time to do that, to follow good practices, you would decouple them and just connect them using messaging. But initially, because it was initially a monolith and no one designed modules to be autonomous, there is always some shared state in monolith. You can help yourself from that. So when you decouple them from monolith, you take away a microservice, you can initially rely on the shared state and then gradually improve it so that you can communicate the states across messaging and don't rely on the cluster. But the cluster helps you to get there. In the end, you would have something like that. Once not so frequently used service on the server or the monolith, and the frequently used services you need to scale up will be run on multiple nodes. There are some other features of Hazelcast which might be interesting. One of them is enterprise feature. It's quite interesting if you really want to optimize the usage of memory, and that's of heap data storage. Hazelcast can remove the data from the heap and put it, highly optimize it and put it on a system memory and manage it in their way, so it's much, it contains, requires less memory, because Java is not so good in managing memory. And Hazelcast also provides features like automatic discovery, so that when you start up instances, if you saw I only executed the same command line in Payara Micro and it automatically connected to the cluster, I didn't need to configure anything. They automatically discovered each other. So that's done by Hazelcast. And that's configurable. It can use multicast to automatically discover, or there are plugins for Kubernetes, for AWS environment, to get the IP addresses from the environment and connect to the cluster. If you have any questions, feel free to ask. For use cases for cache, for caching? Cache is mainly used to speed up performance and distribute the memory. So you can use it in some limited way for some other things like passing data across the cluster, but it's better to use some other mechanism on top of Hazelcast specific features or some other data tools features. But one thing I use in my application is to use it for locking. They can also specify distributed locks, so you can use the lock, and on the other side you would basically find out that the log is logged and would either ignore the message that came or just wait for the log to be unlocked. And there are some other features in JCache which are beyond caching, but mostly you will want to do it for caching. And Payara server is very easy to really speed up the performance just by this catch result annotation, which automatically puts the arguments of the method into cache and the result into cache, so that when you call it twice, it won't call the method, it will just return the result. And it's one annotation, so not much coding. And otherwise, caching is just a start to get some data into memory, to distribute it. Then when you want to grow your application and design it further, you would either use some other features of Hazelcast or the data grid that provides the distributed memory via a server uses them to distribute the HTTP session and all the Java stuff. So if you use these, you will get it for free because you just use HTTP session, put everything to it, and it's suddenly on the other nodes. So with file server, it's quite easy to do, but it doesn't use Jcache. It uses the Hazelcast queues to distribute the data. So Jcache is just an interface to somehow interact with the data, but it's for caching. So it means one thing that limits Jcache is that the data won't be there eternally, won't persist there, because it's cached and the implementation can remove them at any time. You should design it just for speeding up, for temporary memory. If you want eternal memory, you have to use maps from Hazelcast, where you can also specify when the items should go out, but it will remain there. For example, in my application, when I try to edit 1,000 items into cache, it always remained around at 10,000. So 100,000 were being edited, but in the meantime, 90,000 were removed. So at the end, I couldn't get more than 10,000. When I put them into memory, into map, the 100,000 remained there. So I can use map, or you can use map as a database, while if you only use Jcache interface, it's for temporary storage to speed up the database. You can extend Jcache when you add read-through and write-through listeners. So then every time the implementation removes something from the cache, you can get this as a message, as a notification, and store it somewhere. So that's a way how to persist the data in the cache. But I don't have any experience in there. I can only imagine it could be used first as a cache, but then moving all the data from cache to the database. So it would be like a proxy. You would interact with the cache, and every time when something is moved from the cache, it's put somewhere else. But every time it's accessed through the cache and it isn't there, then the read-through mechanism would transparently go to the database and put it into cache, and it would appear as if it is in the cache. So in this way, you can make the cache eternal, but the data wouldn't be stored always in the cache. It will be like passivated into a persistent database, and if it's not there, it will be then activated. But you have to do it yourself just by injecting something for reading the data and for writing the data. Yeah. Yes, I understand. I think I understand. The question is how to configure the time after which the cache data is evicted, removed from the cache. This is the terminology in Jcache is so-called policy. Policies, eviction policies. Eviction means removal from cache, and you can specify your class, which implements an interface and specifies this policy. And there are also prepared classes in Jcache to specify the removal after some time. The item is added to cache. You can also tweak this so that not only every time you access the item from the cache, the period is extended. So these are modify and create eviction policies. And you can also create your own policy, so you can make it very complex. And these, I think they can be also added to the annotation, but they are normally part of the configuration when you create the map, create the cache. There's the expiry policy factory class. So this is an argument to the annotation, where you don't specify the policy, but the factory. The reason for the factory is that the policy has to be distributed to all the clusters, so it has to be recreated on every cluster. That's why we create factory, which should be serializable, but the policy doesn't have to be serializable. Only the factory card is serializable, so the code is serializable, and it's executed to create a policy on every node. So it's a bit complex, but it requires basically two classes to implement. One is the factory, and there are always prepared builders in JKS specifications, so you usually don't have to create classes, you just have to reference them or extend them to specify this behavior. So that's everything. That's everything from me. I'm happy that you came to my session. I hope you enjoyed it. If you want to have some stickers or t-shirts of Payara, you're free to come and